video, we will be explaining how to model the cosine theta coil in Rat. The cosine theta coil is a coil that's mainly used for accelerator physics, so dipoles and quadrupoles in large accelerator complexes like CERN, for instance. And the way that Rat models the coil is based on the detailed description in Dr. Ruschenschuk's book, Field Computation for Accelerator Magnets, the first edition. And in chapter 19, you will find the mathematical description of the cosine theta coil, the constant perimeter coil end. And that description is what is used in Rat to model these coils. So for more information on how to make such a coil, you should look into that book. In Rat, you start a cosine theta coil by making a custom coil first, and then the path defines the cosine theta shape. So set path cosine theta will give you that shape. And of course, you need to select a cross section. In this case, we'll use a wedge. And the reason for that is because the wedge shape kind of resembles the keystoning that many cables used in cosine theta coils may have. So this is an example here of a wedge shape, and it's defined with a different inner and a different outer thickness. So then this is the shorter one and that's the longer one, and that's how you get a wedge. But before you can actually see something, you will be required, you see that the cosine theta path doesn't have a lot of settings, just the discretization, so the element size along the path, and the lead end, which defines, or which will tell Rat if you need to connect the 2 or 3 different blocks, or if you want to have them as continuous loops. So in order to make the actual path, you need to add a block. Cosine theta coils are usually made with different blocks along the cylinder on which they are shaped, and the block then has all the parameters of the cosine theta coil. For reference, I will quickly add a cylinder. This will show you sort of the beam pipe that we are modeling the coil on, and then you immediately see the first important thing that you need to set. The cylinder here has a radius of 25 millimeters, and actually the radius of the cylinder on which we are modeling the path also is 25. So the way that the path is defined is on the outside of the cable, and the reason for that is that if you would define it on the inside, you would get more edge regression because your cable is a rectangle, it's not a line, an infinitely thin line, and so you run into trouble in your coil ends. So it's easier to define the cable on the outside to avoid having more edge regression than necessary, but that means you need to also define your cross section on the inside. And moreover, the cable dimensions of your cross-section need to be copied in the settings for the cosine theta block. This is because you can have wedges or rectangles and even circles, and Rat doesn't automatically copy the settings of your cross-section over to the settings of the cosine theta block. So in this case, our wedge is 2 by 2.2 millimeter in the normal direction. So that's the thickness. So we need to copy that here in the cable dimensions of the cosine theta. Now again, since the path is defined here on the outside, on the wedge you need to define the thickness, the transverse thickness, on the inside. So you need to start from -10 if your thickness of your cable is 10. So here your cable thickness is just set as a number, 10, and then you need to start at -10 to 0 to make sure the path and the cross section are aligned properly, and then you see that it perfectly touches this 25 millimeter radius circle or cylinder. The other setting here is the insulation thickness. So if you set an insulation thickness of 0.5, the cables are spaced differently. So let me set it back to 0. If they're 0, they're completely touching, but you might have insulation. If you set it to 0.5, there is a 1 millimeter gap here because each cable is wrapped with 0.5 millimeter insulation, right? So this gap here now is 1 millimeter. If you want the gap to be 0.5, then you need to change the insulation thickness to half that. So that's the cable settings that are in the cosine theta block. And now let's go look at the other settings. So the number of turns, I guess, speaks for itself. It's just the number of turns in this block, so you can vary that accordingly. The number of poles defines whether this is a quadrupole or dipole or so on. You see that if I changed it to 2, that's for a quadrupole, this sort of distance between these two straight sections immediately goes to about a quarter of the cylinder. And that makes sense. So for a dipole, you set it to 1 and then it's sort of half. Phi and alpha define the angles on the straight sections, and I can demonstrate that with this picture over here. So if this is your cylinder again, here in the bottom right, phi defines the position where the first turn of your block starts. So it's always about the first turn. So if you make, in the Rat GUI, if you make this larger, 20, then this moves up. So let's look at it here. A 0, it's completely in the middle, and a phi of 25 is obviously starting higher, and it's the first turn that defines the starting point. Alpha, on the other hand, defines the rotation of the cross-section, so the rotation of your cable with respect to it being completely flat with the horizon. So if we go back to our model here, if we set alpha to 25, you see immediately that there is an angle here now. So back to 0, it's flat with the horizon, and 25 turns it up. So I'm going to set this back to 0. That's maybe more simple later on. So that's all this. The radius, again, determines the inner radius of where the cable is touching. Our cylinder was 25, so I keep this to 25. And this was for the straight, phi and alpha is for a straight section. And now let's look at the 3D coil end. And that's really where your cosine theta coil gets its constant perimeter coil end from. Let's assume there's no wedges. If there's no wedges, which is the default, there is no spacing in between the coil end turns. So if I set this to 0, these cables are touching here in the middle at the coil end. Let me in fact put a clip group so that we can see, there you go, it's on the other end, so that we can see what the coil end looks like. And I'm going to add a few more turns to here so that we can see this. And let me make our cylinder a appropriate length. Oh, yeah, there you go. So that you can see, is there an insulation thickness? No. So that you can see here that this is your cylinder. And the cables are now completely touching because in our block we have no wedges. If you do set wedges, then there is some space here, you see, in between the turns on the coil end. And this basically makes each turns hardware band free. Now, that's not the goal usually when you're making this coil. Usually you just want to minimize the number of space that you need and push the cables together. That does mean that only the first one is limited in hardware bending. These other ones, these other cables, have way more hardware bending than this one because you're pushing them towards the first turn. But that's usually okay because these rectangles are actually cables of individual wires. And usually it's okay. There's enough flexibility to allow for hardware bend. So what other settings here are in the coil end? That's lambda, which basically defines the amount of ellipse shape that you have here in your coil end. And we can look at the coil end settings by going to the next slide here. So in equation 19.50 from Kuschenschuk's book, this is the definition of your coil end. And lambda here, this setting is basically the ratio between B and A. And B is this parameter here, and A shows up here. And that defines how much of an ellipse this shape is. So let me edit node ungroup. And if I go back to the block settings and I increase lambda, you see that this will become more elliptical. Let's go back to 1. The nose here is the position of where the nose starts, defined on the inside here from the center of the coil. So I can demonstrate that by making this cylinder 500 long, because if I look here, the Z nose is 200. And if I go to view orthographic, meaning there's no perspective, and I can set the Y normal. Yeah, you see that if you zoom in here, oops, that the end of the cylinder sort of matches. Maybe I should have a bit smaller element size. The end of the cylinder, we can even make the cylinder much bigger, and then you see it stick out. 40? Yeah, there you go. The Z nose is touching here with the end of the cylinder. So it's how the where the nose starts from the center of the coil. Let's turn this back to 25 and back to the block. Beta is, we should look at it in this way again. So make the cylinder 600 to stick out, and here I will make a clip again, because the beta defines the angle of the cable on the coil end. And if I set beta here to 90, you will see that the first turn is completely vertical. So if you make this to 50, the first turn, yeah, that has an angle. So that's the angle beta. And then finally you have these two settings, N1 and N2. Those are from this equation over here. This is N1 in this exponent, and N1 and N2 is over here. And that allows you to even tune the shape of the coil end more finely. So it's a very fine tuning sort of settings. N1, you will have a bit more freedom. You won't easily break the shape. N2, however, oh, this is fine. But there you go. With varying N2, as you can see here, you can very easily break the coil shape. So you have a bit less flexibility here. It defines the coil end shape. You can play with these. Take care that, you know, beware that there's not a large difference that you can change these with. You can influence the shape of the coil end with N1 and N2. You see the shape here is, you're basically pushing it, you're pushing this flatter here, this piece. If I go back to 2, this is more, this starts to go up earlier than when this was 3.5. This is more flat. But you will potentially have, let's toggle the mesh. You will potentially have more edge regression. So you need to be careful when looking at your mesh that you actually have a shape that is still sort of okay. So that's N1 and N2. Now that we have all this, let's turn my mesh off. We need to actually make this into an actual dipole, because orthographic view is still on. I think you saw that maybe. Turning this into an actual dipole, meaning there is also the bottom part of the coil, you can do that by placing your custom coil in an angular array. Now make sure that for the base orientation, which is how your azimuth of your coil is defined, is set to Y, and the number of symmetries important. So for a dipole, you only want 2 symmetries, because it's a dipole, so you have a top and a bottom part. If you add more blocks here, and you change this to 25, this to 30, then this one also needs to be shorter, right? If you add more blocks here, they will just, since they're in the same group, they will be added to both sides. Now in the cosine theta path, we had lead end, and you see here that this sort of end here has a connection to the other block. If you turn this off, it's disappearing. Then we just make loops. So lead end will try to find a way to connect the blocks together. Then how would we go about making a quadrupole? Well, as I said already, first you need to make 2 poles, and then in your angular array you need to change the number of symmetries to 4 in order to get your quadrupole. Another very important setting in the angular array is the alternate direction, which you need to turn on. This changes the current direction for this top half and that top half, because otherwise, if we look at the plane calculation, plane, custom coil needs to have some current. If I now go and calculate the plane, oh, I completely calculated the wrong plane, excuse me. 150, 150. If we calculate the plane now, you will have a proper dipole, hopefully. In fact, actually, yes. Here we have a dipole, so we have one direction. If in the angular array we don't turn this on, and I repeat the plane calculation, then you will have a quadrupole because they will be powered in the same way. You see? Yeah, it's a bit purple here. I could change. I changed the colors. But you see there's a quadrupole now instead of a dipole. So you need to make sure that in the angular array you check alternate direction, and then you get a change of current for the different sides of your coil. Let's see. I think this is the end of the tutorial. This is how you create a cosine theta coil in Rat, and we're looking forward to seeing you in the next video. Bye bye!